Hello friends, good morning. In today's lecture, I will explain what are the different ratings of lightning arrestor and how they are selected. So once again, I will repeat or in brief discuss these two basic waveforms. First one is voltage versus time in microsecond, voltage in kV, and second is current versus time. Obviously, time is in microseconds and current is in kiloamperes. First thing here is BIL, that is basic impulse level or basic impulse insulation level or basic insulation level. It is defined as the peak value of standard 1.2 by 50 microsecond impulse wave which the insulation of the system or insulation of the equipment can sustain. So that is defined for the system as well as for the equipment. Now we are using lightning arrestor to protect the instrument. In this diagram, this is the transformer. So for this transformer, let us say this is the BIL. So when lightning or voltage comes, it must when the lightning or voltage comes, the lightning arrestor must discharge this lightning or voltage before it attains the BIL. So we have to keep the spark or voltage of this lightning arrestor, impulse spark or voltage of this lightning arrestor well below the BIL. So let us say this is the lightning or voltage coming at this value, that is impulse spark or voltage. The lightning arrestor sparks over. So there will be discharge of lightning current. So as soon as it sparks over, the discharge current starts flowing. So there is sudden reduction in the voltage, then current as well as voltage both are increasing, then both start reducing, and finally the lightning or voltage is discharged. So this is the mechanism. So from this diagram, we can say that there are four basic ratings of the lightning arrestor. Along with these four ratings, there will be other ratings also. So from these diagrams, we can define four ratings. Number one, this is impulse spark or voltage. This results into flow of discharge current. So second is discharge current. Third, when discharge current is increasing, it will attain some peak value, so that is maximum discharge current, and corresponding to this, there will be discharge voltage, that is also called as residual voltage. So these are the four important ratings. Along with these four ratings, there are two more ratings. Out of those two, the first one is called as rated or nominal voltage. We denote this by V rated, and second is power frequency spark or voltage. So today I will discuss first two ratings, that is rated or nominal voltage, and second power frequency spark over voltage. Now let us see the definition of rated or nominal voltage of the lightning arrestor. It is the maximum RMS power frequency voltage which the lightning arrestor should sustain across its terminals without damaging to any part when power frequency follow-up current is flowing. So here new term is coming, that is follow current or follow-up current. Well, let us see what is this power frequency follow-up current, or in general, what is this follow-up current. Again, this diagram. When there is no lightning or voltage, the system is operating in steady state and power is flowing from generator towards the load. So there will be flow of the current. Now this lightning arrestor is adjusted in such a way that during power frequency voltage, there is no spark over. Now when lightning over voltage comes, this gap breaks down and there is flow of discharge current. Now when this gap breaks down, we can say that there is short circuit. So there is short circuit, so discharge current is flowing, that is impulsive in nature. Along with this discharge current, power frequency current is also flowing. So this power frequency current is called as follow-up current. So lightning arrestor has to interrupt not only the discharge current, but this follow-up current also. Not only it has to interrupt, but before interruption, it has to carry this discharge current as well as power frequency current. So impulse voltage is also appearing across this lightning arrestor, that is called as discharge voltage, as well as some power frequency voltage is also appearing across this. So that power frequency voltage, the lightning arrestor terminal must be capable of withstanding. So the definition is, it is the maximum RMS power frequency voltage which the lightning arrestor must be capable of sustaining without damage to any of its part by interrupting and carrying the power frequency current. It is defined in kV and it is rated in terms of line to ground voltage. It is rated in terms of line to ground voltage. So that is the first rating, that is rated or nominal voltage. Now let us see how it is selected. For selecting the rated voltage of the lightning arrestor, this equation is used. Rated voltage of the lightning arrestor is Ke into VMOP. K is called as coefficient of earthing and this is called as maximum operating voltage of the system. Now I will define these two terms. First, maximum operating voltage of the system. It is 1.005 to 1.1 into system voltage. Now, if we consider system up to 220 kV, then we take the multiplying factor 1.1. When system voltage is up to 220 kV, we take the multiplying factor 1.1. So for example, if it is 132 kV system, then this maximum operating voltage will be 1.1 into 132. That is approximately 145 kV. If it is 220 kV system, then it is 1.1 into 220. So that is 242 kV. But if system voltage is above 220 kV, then this multiplying factor is 1.05. So for example, if we are considering 400 kV system, then it is 400 into 1.05, that is 420 kV. So in this way, this maximum operating voltage is computed. This maximum operating voltage is nothing but the maximum value of the power frequency voltage the system insulation can sustain continuously. So that is maximum operating voltage. So if it is 400 kV system, the power frequency voltage rating of the system will be of the insulation of the system will be 420 kV, means it can sustain continuously 420 kV. So that is how this rated or nominal voltage is calculated. So this is clear. Now I will define this coefficient of earthing. So next I will define and discuss Ke, that is coefficient of earthing. This coefficient of earthing basically depends on how system neutral is earth, that is how system neutral is grounded. Now depending on the method of grounding, the coefficient of earthing or system is divided into three categories. Number one is effectively grounded system, number two, non-effectively grounded system, and number three, ungrounded system. Now let us see what is effectively grounded system. As per definition, the system in which under fault condition, the line to ground voltage of the healthy phase does not exceed 80% of line to line system voltage, that is called as effectively grounded system. I will repeat. It is the system in which during fault condition the line to ground voltage of healthy phase, suppose A, B, C phases are there and there is fault of B and C grounded, or simply B to C, or P grounded or C grounded. So if it is B grounded or BC fault, then phase A will be healthy phase. So in that case, we consider the line to ground voltage of the A phase. That is, during fault condition, the line to ground voltage of the healthy phase does not exceed 80% of the line to line system voltage. Then such systems are called as effectively grounded system. And if system neutral is solidly grounded, then the line to ground voltage of the healthy phase during fault condition does not exceed the 80% of line to line voltage. So in general, we can say that if system neutral is solidly grounded, we say that it is effectively earthed or effectively grounded system. For such systems, coefficient of earthing is 0.8. If it is effectively grounded system or effectively earthed system, the Ke, that is coefficient of earthing, is 0.8. Second is non-effectively grounded system. As per definition, these are the systems in which during fault condition, the line to ground voltage of healthy phase can exceed 80% of the system line to line voltage, but it is less than or equal to 100% of line to line system voltage. Such systems are called as non-effectively grounded systems. And if system neutral is grounded through some resistance or it is grounded through Peterson coil, that is arc suppression coil, then the line to ground voltage of the healthy phase is in between 80% to 100% of line to line system voltage during fault condition. For such systems, we take Ke, that is coefficient of earthing, is equal to 1. And last one is ungrounded system. These are the systems in which the line to ground voltage of healthy phase during fault condition can exceed 100% of system line to line voltage. And if system neutral is not grounded, then in such case, the line to ground voltage of healthy phase can exceed 100% of line to line system voltage. For such systems also, we take coefficient of earthing is equal to 1. Now I will explain how this is affecting the rated voltage of lightning arrestor. So let us take example of 400 kV. System voltage is 400 kV. First case, it is effectively grounded system, means system neutral is solidly grounded. So in this case, coefficient of earthing is 0.8. So as per the equation for finding the rated voltage of lightning arrestor, it is Ke into maximum operating voltage of the system. So maximum operating voltage will be 1.05 into 400 multiplied by coefficient of earthing, that is 0.8. It is coming 336 kV. Now suppose system is ungrounded or it is non-effectively grounded. In that case, Ke is 1. So rated voltage is coming 1 into 1.05 into 400, that is 420 kV. Now you can see the difference. If system is effectively grounded, the rated voltage of the lightning arrestor is 336 kV. If it is ungrounded or non-effectively grounded, then it is 420 kV. So there is considerable increase in the rated voltage. So if there is increase in the rated voltage rating, obviously the cost of the lightning arrestor will be more. So this is called as 80% lightning arrestor. It is called as 100% lightning arrestor. So that is all about the first rating, that is rated voltage or nominal voltage of lightning arrestor. Second rating is power frequency spark or voltage. Definition is simple. It is the power frequency voltage at which the lightning arrestor sparks on. So it is power frequency voltage at which the lightning arrestor sparks on. That is simple definition. Now, how to select this power frequency spark over voltage rating? So formula is this. Power frequency spark over voltage of the lightning arrestor is 1.6 times V system. So we multiply the system voltage by 1.6. That is the power frequency spark over voltage. So this is second rating. Remaining ratings I will discuss in my next class. Friends, if you feel this lecture useful, then please like it. Subscribe to my channel for upcoming lectures on high voltage engineering and power system protection. Ask your friends, your colleagues, your juniors to subscribe to this channel for upcoming lectures on high voltage engineering and power system protection. If you want to make efficient and effective use of time, then read my book on time management. The link for the book is given in the description box. I have launched one useful course on Udemy, that is Boost Your Learning and Become Top Achiever. This course is very useful to the students as well as and specifically for the students who are preparing for the competitive and entrance exams. The link for the course is also given in the description box. Thank you.